Hi friends, welcome to another session. Now let us see the shortest remaining time first scheduling algorithm. This is a preemptive version of the shortage of first algorithm. The shortage of first algorithm which we had seen in the previous session was a non-preemptive type of algorithm, and this one is a preemptive type of algorithm. It is a core concept in the advanced CPU, and the process with the shortest remaining burst time is selected for the next running. So the properties, it's a preemptive. So if a new process arrives with a shorter burst time than the one which is currently running, the CPU is preempted and the new process is given the chance. We need to have a dynamic scheduling. The scheduler must constantly keep track of remaining burst times and then keep adjusting them in the ascending order. So that's a little overburdened. The goal is to minimize the average waiting time and the turnaround time. And yes, there is risk of starvation if the processes are longer. So every time a process arrives or a process completes, the scheduler compares the remaining burst times of all processes in the ready queue and picks the one with the shortest remaining time. So whenever a new process comes in, it just checks what is the remaining time for the current process, what is the remaining time for the current process, and what is the smallest time in the list. So if the remaining time of the running process is smaller than the smallest in the list, then it is continued. Otherwise, the smallest burst time process gets in and starts running. So this preempts the current process if whenever required. So take up an example. We have 4 processes with their arrival times and the burst times 8495, arrival times 0, 1, 2, 3. And if we look at what happens at 0, only P1 was available with 8 burst times, so it starts executing P1. But at 1, 4 P2 comes in with a remaining time 4, so it starts executing. At 2, another process with burst time 9 comes in, so at slot 2 there are 3 processes in the list. One currently running has completed 1 session, has 3 more sessions to continue, and P1 1 session taken up, 7 more required, and freshly come P3 needs 9. So out of this, P2 requires only 3, that's the shortest, so P2 continues. The third slot P2 continues, fourth slot also P2 continues. So this way the P2 completes its 4 slots at 2, 3, 4 and 5. At 5 it just checks. By that time the P3 also come at 3, and now at 5 this is having 3, then P3 is having 9, P1 is having 7, so 5 is the smallest, so P4 comes in picture now, and this is 5, this is 9, this is 7, 5 becomes 4, then 4 becomes 3, 3 becomes 2, 2 becomes 1, 1 becomes 0, till then it is smaller than 9 and 7, therefore P4 continues. And once P4 is done, then we are left with P1 and P3. P1 requires 7, P3 requires 9, so 7, 9, so P1 wins, 7 becomes 6, 6, 5, 4, 3, 2, 1, 0. Till then this P3 requires 9 and P1 requires less than 9, so P1 continues, and finally if none of them is available except P3, then P3 gets its chance. So let's look at the whole scenario. So at 0 time stamp, only P1 was available, therefore P1 starts working, and after 1 slot 7 are remaining, and after 1 slot P2 comes in, and which requires 4 units of time, so P2 is given chance because P1 needs 7, P2 requires 3, and after one slot P2 requires 3 more, so 3 and 7, 3 is small, so P2 again, 2 and 7, P2 is small again, 1 and 7, P2 is small again. Finally P2 completes its work, and by that time P3 P4 also have joined the list, and P3 was 9 and P4 was 5, and when P4 joined it was at 3, and at that time P2 was 1, P1 was 7, therefore P2 wins the race. So fourth slot also P2 takes up and completes its job. Then comes P4, 1 slot, 2 slot, 3 slot, 4 slot, 5 slots, because as long as P4 is working we are left with P1 with 7 and P3 with 9, which is bigger than 5, 4, 3, 2, 1, 0, so P4 continues to run, and once that is done we are left with two more processes, P1 and P3. P1 requires 7 and P3 requires 9, so P1 wins the race. So 7, 9, so P1, then 6, 9, P1, 5, 9, P1, 4, 9, P1, 3, 9, P1, 2, 9, P1, 1, 9, P1 finally completes, P1 completes its task, and it's left with only P3, therefore P3 continues to execute for all the next 9 slots. Now if we look at the situation, it looks like this. So first slot P1 occupies, then next 4 slots P2 occupies, then next 5 slots P4 occupies, then next 7 slots P1 occupies, and finally 9 slots P3 occupies. So if we look at the situation, then if we look for the various times, let's look at P1 waiting. So P1 is second slot is working from 10 onwards, then for first slot it is P1, then second slot to 9th slot it is second slot to the 10th slot it is P2 and P4, so P1 is waiting in this period, so totally 9 units of time P1 will be waiting, and turnaround time, that is P1 completes its action at 17 and P1 comes at 0, and at 0 it starts execution. That means CPU gives its chance to P1 the moment P1 comes in, therefore the response time is 0. Now looking for P2 arrives at 1, therefore it starts at 1 and it completes its total thing, so there is nothing for P2 to wait, and P2 turnaround time is 4 units because it has come at 1 and completed at 5, so total 4 units of time, so its actual time is 4, turnaround time is also 4. That means P2 has got a full attention of CPU and wonderfully done its job. As far as response time is concerned, P2 has come at 1 and P2 starts working at 1, therefore response time is also 0. Now looking for P3 has come at 2 and P3 starts working at 17, so 17 minus 2, so for 15 units of time it had to wait to get its chance, and the turnaround time, it has come at 2, completes at 26, therefore it takes 24 units of time to complete its work from the time it has come in. And looking at the response time, it came at 2 and it started running at 17, therefore 15 units of time was the response time for P3. And as far as P4 is concerned, it has come at 3 and it starts working at 5, therefore 2 units of time it had to wait, and then P4 completed at 10, it had come at 3, so it should have been 7, sorry, so the turnaround time is 7 units, and response time it had come at 3 and it was recognized at 5, so the response time is 2. So the average is 6.5 waiting time, somewhere less than around 12 for the turnaround time, and 4.25 is the response time. So this gives almost best solutions for all parameters. So the advantage of using this algorithm is minimum average waiting time, efficient CPU utilization. So CPU is never waiting for any other whenever any process goes on waiting for some IO and all that, then we can allot this. So CPU utilization is a better, faster turnaround time for the shortage jobs. Yes, the shortage jobs are given chance first, therefore the moment they come in, they possibly get the chance to run, therefore turnaround time is as small as possible, reduces turnaround time. On the other side, the disadvantages, yes, starvation, because we have a dynamic list now for scheduling, and as the scheduling continues and if the new processes with the smaller burst times keep coming in, then the process with the longer burst times have to keep waiting and waiting and waiting, and if this keeps happening forever, then the one with the longer burst time have to wait forever. So there is a risk of starvation, and before using this algorithm we must perfectly know how much is the burst time of each task. So a very accurate prediction is required for each burst time, and it's a little difficult to make sure, because our processes usually may contain some loops and all that, and just we cannot statically say that what is the number of times the loop can take up and all that. So it may vary from situation to situation. The same process running twice may take different durations to complete depending on many issues, like human interaction, like the inputs read from the external sources, IO devices and all that. So depending on many issues, the duration of the process keeps varying, and hence it's very difficult to implement this type of algorithm, and we do have a very high overhead, because the ready list has to be updated every now and then, and every time a new process comes in picture, the whole list has to be sorted so that the shortest comes first. So the sorting has to be done at a regular interval, or every time a new process comes in or old process goes out, then the whole scheduling has to be redone and all that, and because of this lot of overhead will be there in the shortest remaining time first type of scheduling, and it is quite high, quite a complex situation when it comes to implementation. So that's it about the shortest remaining time first scheduling algorithm. More details, more types of algorithms to continue in the coming sessions, so keep watching. If you find this session of any use, please don't forget to like, comment, share, and please join us by subscribing to this channel. Thank you.